Well, I've got. If you don't have any questions, I've got one thing to show you. So.
Okay.
Yeah. Do you want to start with any questions you guys have?
So, I guess maybe we don't have any immediate questions, but we are interested in the fabrication sort of process. I'm sure this will come later in the course, like preparing the layout and what specs you have, and then in addition, I'm personally interested in the possibility of perhaps getting another fabrication run done after the course, right? For students who have research projects that they'd like to pursue.
Absolutely. Yeah.
And coordinating with you how to do that.
Okay. Yes, I can speak to that in sort of a short summary form. So next Tuesday, the module that we start on is the layout portion. So for the next 2 weeks, we're going to be doing drawing the geometries, and in there I provide the minimum information on the fabrication process that you need to design into this technology. So specifically, what's the minimum feature size we specify as being 60 nanometers. But other than that, we just assume that anything you draw will be 220 nanometers thick, and anything you don't draw is etched away, and then we have oxides surrounding the whole structure. So that said, the week after you submit your design, which takes us to March 5th, I guess, that week we're going to go into the details of the fabrication, like all the electron beam lithography, the resist, and all that kind of stuff. So there's a lot more detail there, but I kind of put it on afterwards as opposed to beforehand because it's not prerequisite material. In terms of doing additional fabrication runs, so we go through University of Washington as well as Applied Nanotools. In the case of University of Washington, the way it works is university needs to create a relationship with them through they have a contract kind of thing that they look for. In the case of Applied Nanotools, they have an online credit system, so it's fairly easy. So you pay your $1,500 or $1,000, whatever it is, and then you upload the file directly to them. So in both cases, the chip size you get for on the order of, like I said, $1,000, $1,500. The chip you get is 9 by 9 millimeters.
Okay.
So it's actually quite a lot of room. So in this course, we set the standard size to be for every student, we give a box of 600 by 400 microns roughly. And then that kind of forces people to kind of squeeze things in compactly and efficiently. And then if people want more space, we say, well, you can upload as many files as you want. So some people have uploaded 20 or 30 files even. And then, so that allows us to fit in this class on that 9 by 9 block, something like 1,000, no, I can't remember. Maybe like 500 designs, something like that.
Okay. So if my students have additional designs or they want to participate in the competition that you've got going, I'm trying to encourage them. They could upload the one that I'm requiring them for the class to do, and then in addition, maybe some other file might get fabricated, space permitting.
Absolutely, yeah, we have lots of space, yeah. So we definitely don't have any space constraints. I mean, if you just kind of do the math, the incremental cost of fabricating one extra design is almost nothing, right? So if you divide there's a fixed cost. And then after that, just adding little blocks doesn't cost us anything. Or almost anything. There's a little bit of extra write time, I guess. But yeah, so in terms of blocks, then I think the assumption is that everybody takes at least one block. And if you need more blocks, you can take as many as you want.
Okay, that's a great update. Okay, because we were wondering how constrained we'd be. Terrific. Now,
and you'll see next week, but within one block, like for example, for the interferometer project, you can fit easily 10 interferometers.
Okay, great. Now, I think I was looking through, maybe it was Applied Nanotools website. They offer, I think, metal layers as well, which won't be part of this class, but is it your experience then that they can offer those for a similar price to?
Yeah, so there's on the Applied Nanotools webpage, they actually have a pretty nice sort of order button where you can type in all the parameters that you want. So they give you choices in terms of, do you want oxide or no oxide, metal, no metal, edge coupling, no edge coupling. So there's a bunch of modules. So I think the incremental cost of getting metallization is on the order of maybe $500 roughly.
Okay.
Or maybe a little bit more, depending on how many metals. So I'm not up to date on what the latest costs and what they offer, but the starting point is a single metal heater, which is maybe a micron or so above the waveguide. And then they've also added an additional metal that's a low resistance metal. So you have a high resistance metal for the heaters, and then a low resistance metal for the routing and for the contacts.
Yeah.
And then they also do an additional step where they passivate the entire chip and open up the electrical pads. So I think that's the most, I don't know if it's the most complicated standard offering that they do.
Sure.
Is those metal heaters that are covered in passivation so that they can withstand higher temperatures.
Okay. And let's see. So most of my class is here now. If you guys have questions, are you on your laptops? You can log in and chat or whatever. All right. Well, we'll turn it back to you, Lucas. Thanks for entertaining our few initial questions.
Sure, yeah. Yeah, so there's a few other people online, so feel free to jump in with questions. So I'll just sort of open up the floor. Does anybody have any questions? And if nobody's going to jump in, I want to talk a little bit about the design competition. I want to the component modeling and the circuit modeling and the layout together. So, okay. So any questions on the discussion forum posted so far? All right. Well, let me jump into what I wanted to show you. So, so for the design competition, one of the challenges for people who are doing first-time design of silicon photonics in this course is that we show you how the components work, and we show you how to connect them together to make a circuit and how to draw them. But what we don't go into is spending 6 months of how to optimize and model all the intricacies of making a really good component. So, for example, the Y branch that we show in the design competition was, there was a PhD student who spent quite a few months optimizing it, learning all the modeling tools to do optimization, parameter optimization. So what I want to show you is not how to do that part, because that's fairly involved. But what I want to show you the part is what happens if you have a design that you're happy with. How do you create the S parameters for that component? And so there's a few questions on the discussion forum where people asked, how do I take my component and generate S parameters for the Y branch, for other things like that? And so so let me just turn over my screen. So I want to basically show you how to go from a design that you can draw in the layout tool, how you can simulate that structure, and then how generate the S parameters, and then bring those S parameters into the circuit modeling tool so that you can perform circuit simulations. Okay, so this is essentially kind of warming people up to the design competition and sort of the how do you evaluate if your component's good or not. Okay, so let me screen share. Okay, so so what you're seeing here is the view of the program called KLayout, which is the one that we will be using next week. So starting next week, I'm going to give you tutorials on how to create these drawings in this program. But basically, this is showing you a component that kind of a dummy component that I made, which consists of an optical input port on the left. So the light comes in, and then the idea here is that this is supposed to be a splitter. So the light comes in from the left. This is a nanotaper. So the idea is that the mode will start expanding as it travels down this little waveguide. And then some of it should couple evanescently to these other nanotapers and then come out of these two other ports. So this is not a good design. What's good about this design is it's very small, so it allows me to demonstrate this kind of real time. I made this extremely compact so that the simulations run quickly. So the requirements for, I guess, the components in terms of that we have in the library are that we have this layer here called the device recognition layer. So the device recognition layer basically defines where the component extent is. Of course, we have our silicon geometries. And then finally, we have these things called pins, and we labeled this as pin rec. And you can see that there are labels here, opt1, opt2, and opt3. So this is a 3-port device. And so what our objective is, how do we take this structure and export it to FDD for circuits, for component simulations? And so what we've actually done is made this easy for people by some of the scripts that I showed in Photonic Components. We've imported those scripts into KLayout. And so KLayout uses Python, but we can take those scripts and then send them over to Lumerical FDD. So the menu item here is called Component FDD Simulations for S parameters and create a compact model. And when you click on this is a bit of a mess, this GUI. I didn't spend too much time on this, but this is a laundry list of some of the parameters that I thought are important. And so specifically in the first week, we talked about convergence testing to make sure your answer is accurate. So I include a simple convergence test in the script. I'm going to disable that to make it go faster right now. We can think about boundary conditions, number of modes. So the design competition asks people to design a component that's suitable for both TE and TM. So this, I tried to write this so that we can simulate both modes. So you can either put in 1, 2, or 1 and 2. I'm just going to show you with the TE polarization. And something else that I'm going to do to speed up the simulation right now is mesh accuracy. So typically for a pretty high accuracy result, I use mesh accuracy 4. But for this demonstration, I'm going to use mesh accuracy 1 so that it can go really quickly. Okay, so basically these are all the parameters that are going to be used to configure my simulation. And oops, let me try that again. I was in the wrong cell. Okay, hopefully my parameters, oh no, they disappeared. Okay, that's too bad. Let me put these back in again. Okay, so what this is doing is it's launching. You can see FDTD is bouncing up and down here. So it's launching FDTD, and then it's going through a script that essentially takes all the polygons that are defined in KLayout, draws them in FDTD, and every port that we've defined, it also injects, it creates one of these ports at the on all three pins defined in the layout tool. So we're using the object called port, which essentially consists of a source as well as a detector or a monitor. A fast FDTD simulation where it's swept as a function of wavelength, and it gives us the transmission from, this is S31, so I think this is injection in port 1, measurement on port 3, and then S21. So you can see this device is not very good. As I preface the discussion, we can see we're getting about a 6 dB, 7 dB insertion loss, but I think it illustrates the concept that you can go from a top view of a device drawn in the layout tool, extruding the structure into a 3-dimensional structure, configuring the FDTD environment, including the perfectly matching layers and other boundary conditions and sources, and then doing the simulation. Now, the next, so the idea is that you look at this simulation, you say, okay, well, this looks like a splitter, and I'm happy with it. The next step is creating S parameters for this, which requires doing, in this case, for the device, doing 3 separate simulations. And so this is what's being simulated right now. You can see it's doing 3 jobs. Each 3 jobs essentially consist of injection on port 1, then it does injection on port 2, and then it does injection on port 3. Let's see if I can. Can I mute one of the microphones I'm hearing? Let's see which one could it be. Let me just mute. Okay. So the result is shown here. This is the visualizer essentially brings up the S parameters. You can see how many S parameters we have here. We have a total of 9 S parameters. So this is a 3x3 matrix. And right now it's plotting the real value of the S parameters. If you want to look at the magnitude, then let's say, for example, S21, we need to switch this to absolute value squared. So the S parameters are in terms of electric field. If you want to know how much power is transmitted, you look at absolute value squared. And this tells you that the splitter that I designed has a 25% splitting efficiency, or insertion loss, essentially. Okay, so these S parameters, now you have a 9x9 matrix, and this is essentially similar to the unit that I showed in the online course for the Y branch, except this one is a little bit more generic in the sense that it can take any arbitrary geometry. KLayout will open interconnect. Hopefully, let's see if it worked. Yes, okay. So what KLayout just did was it took the polygons that are drawn in KLayout and created a little icon. So here you can see the icon that was created to represent our component. And inside this component, I think I can open this, expand. What it did was it created this S parameter object. So I showed you how to import the data files into this component. And so essentially I've just automated that process where the S-parameter file created by FTD is loaded into this S-parameter object in interconnect. And now we have a component that was added into our custom library. So on the far right in the element library, custom SciPic user, you can see I've created the, and what I can do is I can now drag and drop and start creating my own interferometers with my own splitter if I want. And I can characterize this. So if you look in the eBeam library where the version number is, I put an optical network analyzer in here to make it more convenient. So I can connect, for example, my output to the splitter, and the inputs here. For example, let's just characterize the S21 of the device. And if I run the simulation, I should get something similar to what I saw in FTD. Namely, you can see my insertion loss of the device is 6 to 7 dB, as we described earlier. So this device, actually, I should probably also show you the back reflections, because that's very relevant for the kind of things that we're doing here that might give us effects. So now I'm monitoring the reflection from the input port. And you can see here it says gain is -35. So this tells us that the reflectivity, the optical return loss of the component is on the order of -30, -35 decibels. So it's not too bad. It's at least from that perspective. The insertion loss, of course, is atrocious, but it illustrates the concept. And if you want to take this further in terms of the default course project that we have, where you're building an interferometer, you can either go back in K-layout, which was what we're going to be doing next week. You're going to be drawing, you're going to be doing something that's going to look like, let me just show you an example. You might draw an interferometer that looks like this, and you're going to create waveguides. Just quickly sketch what the interferometer might look like. Ignoring some of these errors. So your interferometer essentially will look like two waveguides connecting the splitter. So what I'll show you next week is that you can actually simulate this structure. There's another menu item in here called Simulation, Circuit Simulation of the Numerical Interconnect. Now, we haven't covered this yet, so I don't want to confuse things too much. But since we've talked about how to do circuit simulations and interconnect, let me show you how you would do this here. You could drag and drop all the components in here and build your interferometer like so. So for example, you might have 100 microns. You might have the other one as, let's see, where are my properties? I might make this to be 200 microns. And now I can wire my interferometer. Okay, so we have a mixture of library components that are provided in the PDK, as well as our own components. And hopefully this should give us the interference spectrum. Okay, fantastic, it's working, yay. This is always great when things work, especially live. So now we've built an interferometer using our custom component, as well as the waveguides in the library. And then this is how we are going to be assessing the quality of the performance of the components that people design. Specifically, we're going to build an interferometer. We can check to see what the extinction ratio is, so we can see how even the splitting ratio is. So you can see this component has a very good splitting ratio, so it has a very high extinction ratio. And then, of course, we can look at the insertion loss and see how much insertion loss we have here. I'm hoping most people who will be entering the competition will do much better than the 6 dB that I'm showing here, in which case this insertion loss is much more difficult to measure. So the layouts that we're going to be doing for that, we're going to cascade many of these in order to try to accumulate the loss as much as possible. So, yeah, so that's what I wanted to show. So that's essentially an easy way of starting with a component that you think is pretty good, and then allowing you to do the component simulations, circuit simulations, and then connecting the layout to the circuit simulations as well. So hopefully some people might find this useful. Okay, so does anybody have any questions on what I just talked about? Okay, we got a tough audience today. Why don't we check on see if there's any discussion forum questions that are interesting and worth talking.
Yes, c'est ça, pour pouvoir écrire et déposer.
Yes. Mohammed, is that you?
Yeah, it's me.
Great.
Yeah, how are you?
Good, thanks. Yourself?
Yeah, I'm good, thank you. Actually, I have a question, but not what about you are talking about today. Question about the last week. I couldn't ask it last time. So can I ask it now? Is it fine or
yeah?
Okay.
Yeah.
Yeah. So it is about the quasi TE modes and quasi TM modes in waveguides in silicon. I've seen in the course that quasi TE modes has more losses than quasi TM. Because I mean, losses because of the roughness of the walls, lateral walls. Yeah, but they should have less because the thickness of the silicon waveguide is higher than the width. Sorry, it's the opposite, the other way around. The silicon waveguide is larger than the thickness. The thickness is usually 220. But the width is 500 nanometers. So why do we have this loss? So that we should see more losses for the TM modes, quasi TM modes.
Okay. Yeah. So I think there's two reasons why the losses are bigger for the TE polarization. So the first reason is if you look at where the roughness is primarily on the side of the waveguide, as you mentioned. And so essentially from the top down, the photoresist is patterned in such a way that it ends up leaving a little bit of roughness on top. Those roughness features end up getting transferred and etched into the silicon. And so you have a rough surface, but the top is very smooth. I don't have a very good sense of how smooth the top is, but it's probably a factor of 10 smoother than the side. So that's the first thing, is that any light that interacts with the sides will have more scattering than from the top. Now, what's important about scattering is that actually it's the electric field is the part that interacts with the light, because there's a epsilon is the portion of Maxwell's equation that we're changing through the roughness, right? And so it doesn't matter about the magnetic field; it's actually the electric field component that leads to the scattering. And so what's important is when you do your mode calculations is to look at the plot of not the pointing vector or the magnetic field, but you want to look at the electric field intensity. And what you find out for the two different modes is, in the case of the TE mode, the electric field has a very large spike right at the edge of the side, where the sidewall is, where that roughness is.
Okay.
And so that strong electric field intensity leads to the scattering as that light propagates down the side.
Yeah.
Now, if you do it the other way around, if magnetic, then that strong electric field component is on the top and on the bottom, but that material is much smoother, and so it leads to much less scattering loss.
Okay, yeah, that's very clear. Actually, it makes sense.
Mm-hmm. Yeah. So it's actually it's a very interesting topic you mentioned, and there's a number of papers that people have published on studying theoretically where this comes from. One of the challenges from a modeling perspective is how do we predict what the propagation loss is going to be, and that's not really straightforward. We've done some modeling recently where we figured out a way that might be generic enough, and I'm hoping sometime in the next couple of months we can add this to K-layout if all goes well, where we have a generic E per centimeter predictor. But yeah, a lot of the equations that people have developed work for TE polarization, but not for TM polarization, and so on. And there's also what the magnitude of the roughness is, as well as what are the correlation parameters of the roughness. So there's been a lot of papers where people have studied what the roughness looks like, and it looks fairly consistent across most of the fabrication techniques. So at least we have a starting point in terms of what we can use for guessing those reference parameters. But we don't have any actual direct measurements of those.
Okay.
So
I have another question about the library, the eBeam one, and the last version I couldn't find the coupler, the directional coupler. I found the broadband directional coupler. So was that normal or?
Yeah. So that's a good question. So you're wondering where is the conventional directional coupler? So the conventional directional coupler is almost like a primitive that everybody expects to have in the library, but the problem with those components is that the performance is terrible. It has a very strong wavelength dependence that nobody likes, and so we use them in ring resonators, of course, but just as a splitter, like a 50-50 splitter, I think they're just terrible. So I think we just kind of got rid of it.
Okay.
But that said, I think in K layout there should be a parameterized cell for drawing the directional.
I found it in previous version.
Okay, let me just check right now while we look here to see if it's in here. Yeah, no, you're right. Yeah, so the directional couplers that we have are the ones that are like a half circle with a bus waveguide. But what we don't have is the kind of the standard textbook one where we have two waveguides traveling side by side. Yeah. So yeah, that's an omission in some way intentional, but I guess we could put it back in. Yeah, if you maybe if you can remind me, if you can post an issue on GitHub, there's an issue button. So anytime you have any problems or things that are missing, if you post something, where's the regular directional coupler that's in the textbook? We can put it back in. But yeah, so you asked about the broadband directional coupler. The broadband directional coupler is actually two conventional directional couplers cascaded with a little phase shift section in between that essentially leads to a canceling of the wavelength dependence. So that component essentially takes two directional couplers that have poor wavelength dependence and then results in a sum of the two that is much better than just one by itself.
Okay.
May I ask you, just out of curiosity, what's your interest in the directional coupler? Were you looking, what was out of interest, or you wanted to use it?
No, it was just to follow the course to reproduce the results. In some part of the course, you use the directional coupler, the regular one.
Oh, okay. Okay, my apology. Okay, so yeah, so I'll definitely put it back in then. Okay. Yes.
Yeah, so I got similar close enough results with the broadband one, but it's not exactly the same. So, but
no, you're right. Okay. Yeah. So the broadband one will give you better performance. The broadband one has much closer to 50-50 performance across the whole wavelength range, and the insertion loss is similar. Whereas the regular directional coupler has this crazy wavelength dependence. So.
Yeah, and when we use the in some part of the course, we use the two couplers, symmetry. I forgot the name, but to compensate for the phase between the two split between the two branch outputs of the splitter. I run some simulations, and the most I could get is to reduce the phase to 0.2 pi. Is it still acceptable, or is too much by?
I don't understand sufficiently the question to be able to give you a good answer to that. I don't know if you have.
So if in the Y branch.
Yeah.
The Y branch we have. Sorry, not the Y branch. If we use directional coupler as a Y branch as the splitter, we will have a phase difference between the two outputs. The phase difference is huge.
Yes.
Yeah. To compensate this phase.
In the case of a regular directional coupler, it's 90 degrees.
Yeah, it's 90 degrees. To compensate this phase, we just put another couplers and flip it. Hello?
Yeah. Well, I think I don't know if you're talking about there's a unit that we have on lattice filters and doing point symmetric coupling.
Yeah, exactly. Point symmetric. Yeah.
Yeah, so that's a little bit more involved. I don't know if I can give you a good answer for that. You can't just take two components and cancel that out and get one. So this is really more of a circuit design where if you need to cascade two anyways because you're building an interferometer, you can do a better interferometer by flipping the component than you would if you left it in the same. So imagine if you have like 90% and 10%, and then if you connected the 90% on top again, you'd get a worse interference pattern than if you flip the component.
But is this in practice once the circuit is fabricated? Are we going to fully compensate the effect? When this is a question of reproducibility. I mean, if we put two components that are supposed to be exactly identical, are they going to be really identical on the circuit?
Okay. Yeah. So that's a very good question. I'm tempted to give you a demo of that right now, but that might not work so well. So maybe actually no, I should be able to come up with an example. Okay, so let me share my screen and talk about manufacturing reproducibility. So this is a topic that is going to come up after we submit your design for fabrication, but it is useful to consider this during your design. So I'm just going to see if I can find an example that one of my layouts that I was just playing with yesterday, hopefully. Okay, so this is an example of not what's in the course, but it's still a component. So these are Bragg gratings. And what we have in the Bragg grating is a section. Let me just turn off the pin layer. We have a quarter shift. So what you expect essentially is we're creating a Fabry-Perot cavity connected from one mirror to the other mirror and connected to two grating couplers. So I can perform circuit simulations on this component. I'm going to choose which device I'm going to simulate. I'm going to simulate Bragg 1, which is the one on the left I was showing you. When I run the simulation, that sends the layout to Lumerical Interconnect, and it performs a simulation of what you see. So let me just kind of describe what we're going to see here. We're going to see light injected into one grating coupler, coming out of the other grating coupler. So that gives us the broadband, kind of this funny shape of the grating coupler. Yeah. Then we're going to see light bouncing back and forth between the two components, and that gives us essentially this high quality factor resonator. And finally, we see across from here to here, what I'm highlighting right now, that is the reflection band or the stop band of the Bragg grating of each of these. Now, to answer your question, these two are identical components, and the grating couplers are identical. And the question about manufacturing is what happens if when you in real world, are these going to be perfectly matched to each other or not? So we've developed a Monte Carlo technique. So if you look under simulation, Monte Carlo here, there's an option. And this brings up a dialog which lets you do the simulation numerous times. And the parameters in each run are going to be randomized. So the thickness is going to be randomized as well as the width. And what's special about this Monte Carlo is that we're not treating the wafer as one uniform thickness of 223, for example, but we're assuming that there's some correlation variation of the thickness as happens in the real world. So I'm just going to run this maybe 3 times to show you what happens. So this should do the simulation where it's running the same thing. Let's see, is it doing it? Oh yeah, okay, here it is, yeah. So this is going to run the simulation 3 times with essentially the same wafer, but taking your layout and putting it in different positions across the chip. And what you'd expect, what's included is the thickness and the width and variations. So for example, the grating coupler, you can see that, some of the grating couplers come out the same. One of them is actually shifted dramatically in terms of the central wavelength. And that would be because of the thickness and the width of the features that are involved. And so if you look at the way these grating couplers are built, they have these very small features. And I think this is on the order of nanometers roughly. And what we include in the Monte Carlo simulations is essentially a plus or minus 10 nanometer variation in the width and the thickness. So what you see at the end of the day is these peaks. The central location of these peaks is going to vary. The insertion loss is going to vary, and so on. And so I guess coming back to your original question of the directional coupler, if you have a component that has these that is parameterized from thickness and width, you can do these Monte Carlo simulations, and indeed you see that the performance will not be the same. Hassam has some more thoughts on this, so maybe I can. You want to go ahead?
Yeah. So you were asking if you have like 2 components and you wanted to reverse them, right? So I think you, if the components are splitting the waves by 50%, then you would have a zero phase shift. But if they're not splitting the two waves by 50%, you wouldn't get the zero phase shift. So think about it like building a Malzander interferometer of two couplers, and you're always looking at the cross port instead of the bar. If you're looking at the cross port, you would always have a wavelength where you have like perfectly destructive interference. But at the through port, you would never have perfect destructive interference except if you have 50% 50% splitting. So when you're doing these simulations to see if you have exactly zero phase shift or 100% destructive, it's because you're splitting the waves. So when you split the waves, you have to make sure that when the top wave undergo the top path or the bottom path, they're basically having equal magnitude and power when they're at either port. So answering your question, I think you would have zero phase shift if the splitting is exactly 50%. Does that make sense?
For two cascaded components.
Yes.
Yeah. Yes.
Yeah, it's a vector summation, I guess. So yeah, both the power and the phase matters as well. Yeah. Yeah. Thanks, Osama.
Problems.
Thank you.
Hey, Lucas, I have a follow-up question to Mohammed's question. I very much like the way you've implemented your Monte Carlo simulation capability. I'm wondering if there's also a way to sort of imprint upon the layout sort of a known variation across the wafer in silicon thickness, right? So that right, very often, as you know, when you get these wafers, you dice them up, or you have a full wafer that's some size, you'll get very slight variations. And if you build a large interferometer or cascaded interferometers, you need that to take that into account. That's not exactly random, but maybe known. Is there a way that in using your software you can just tell it where on the wafer what thicknesses are?
Yeah, sure. So so the way we've implemented it is we start with a random Gaussian variable for thickness as a function of position. So it's a very high frequency noise, essentially, for thickness and width across the whole wafer. And then what we do is we do a low pass filtering with an autocorrelation length, so that we have some measurements on the autocorrelation or cross correlation. Anyways, the correlation length, I guess. So we know that if you take two ring resonators and you put them close together, they are very well separate them. They eventually become independent. And they start becoming independent roughly around 4.5 millimeters apart on these chips. And so what we essentially do is create this sort of rough surface that's completely uncorrelated, and we introduce correlation by filtering, by low-pass filtering with a 4.5 millimeter coefficient. And so that essentially gives you this sort of blobby, wavy surface. Now, we don't import that per se, as in we don't say, let's take an experimental wafer, measure it, and then load it into the simulator. Instead, what we're doing is we're creating a virtual wafer where we simulate the wafer and use that. And then what I showed just a few minutes ago is we simulated one wafer, and then we put the circuit in multiple places on the die. For the project for the interferometer course, what you're asking about is if the waveguides split and run in different places, will be thicker, the other will be thinner. It's like going up a hill and the other one's not going on a hill. And so the interference pattern will be different for this particular circuit, whereas if you have a circuit somewhere over here, they might have the opposite effect. So what you'll see is you'll see compression or expansion of this free spectral range depending on where you are on the wafer. If you have, you asked about, is it possible to load some data to do this? I think that the short answer is yes, in principle it is. Right now there's a two-line function that says generate random noise function, and line 2 is filter it. So you could just replace that with load it from some other data source.
Okay.
Do you have an interest? I guess just since you mentioned loading files, like do you have any awareness or measurements or capability to generate some other way of this data file?
Outside of course interest, a research interest in making, say, photonic circuits that need to interfere many signals from many sources, maybe on the millimeter scale, right? And and tracking phase shifts accurately is a very hard problem before fabrication. And so typically, right, what's the largest size sort of network you could expect to make without active phase shifts and still have your correlation show up? And so can we, how well can we do in terms of pre-measurement and then design?
Yeah, that's a good question. I mean, let's see. So one example I can give you is we made a transceiver, a communication with ring modulators. So these were ring modulators that are placed as close as possible together. I forget the distance, but they're maybe a few hundred microns apart. So this is like a 4-channel transceiver. And when they're spaced close enough apart, then those rings, and they're all, by the way, the rings are slightly different. And so when you actually look at the optical spectrums, the rings come out, you know which one's which. If you take this circuit and stretch it out quite a bit further, these peaks would start kind of overlapping, and you'd have a mess, and you need thermal tuning to get it to work. But come back to your original question of how big can you make the circuit before you need thermal tuners? Really, anything beyond 50 microns, I think needs a tuner. So even 2 ring resonators, for example, if you're trying to make a filter where you have like a Vernier filter, 2 rings. I remember one of the first projects we did. This was Robbie, who was doing a Vernier filter. He wanted to do a 4 rings cascaded filter. And I told him this is never going to work because of manufacturing variability. And indeed, he made some devices that had 2 rings, and the ones with 2 rings worked, but everything else didn't. And even then he had to make 1,000 variations and just to find that one that worked. So realistically, I think anytime you have things that are very critical to phase errors, you're going to need thermal tuners. I think the unfortunate, that my personal our group's kind of philosophy these days is that we put heaters everywhere, and we come up with ridiculously absurd circuits where we have 60 electrodes coming down on the chip and trying to automatically stabilize everything. And if you have a process where you have monolithic electronic integration, I don't think it's too much of a stretch to have a small PID loop connected to every single critical component in the phase shift. But I think the starting point to all this is really understanding where you need them and where you don't need them. And this is where the Monte Carlo that I showed you can give us some insight into which waveguides are critical and which ones aren't. And then, if it's something that is sensitive and you see that manufacturing variability, is it going to kill your design or not? I'll give you another example where this actually worked in our favor. We created a design similar to the Bragg gratings I was just showing now, except we had 3 sections of Bragg grating. So essentially it was a dual cavity design, whereas cavity 1, cavity 2 coupled through a Bragg grating. So imagine coupled resonators. And we simulated a spectrum, and it looked like it was going to be working. And we got the device back, and we measured basically just a total flat spectrum, nothing there. And we said, what the heck, where did the resonators go? They didn't work. And it essentially turns out that those resonators kind of cancel each other out in magnitude. But when we measured them in terms of the phase, there was a really interesting pi transition at that, or 2 pi even, I can't remember, whatever the pi was, but there was a phase transition at the resonance, but in the amplitude spectrum, you didn't see the peak. And so this was something that we didn't know ahead of time. We designed it, but manufacturing essentially, broke our design. But it turned out that design actually turned out to be useful for Hilbert transformers. And so then that kind of got us into making microwave photonic Hilbert transformers. And it was strictly a result of the being poor that led to a really interesting result. So the opposite can happen. But since then we've learned the origin of that. And now in the Monte Carlo simulations, if you do that specific design and simulate it many times, sometimes you'll see a dip, sometimes you don't see a dip. So and then you can control that. Now that we know how to do it, we can say, okay, well, let's put a heater on that so that we can actually reliably adjust the magnitude of the dip. So, does that give some idea of my thoughts on that?
Yeah, sure. I'm kind of specifically wondering whether traveling wave structures might be possible to extend the range from our 50 microns to maybe a little bit more, since right, you don't have light circulating again and again and again around the same structure and building up that phase index. But maybe if you just have one waveguide and it's going across a chip in some way, and you just want to track the phase in some way, and then interfere it so you look at it. If there's is it crazy to think that you could perform measurements on your wafer thickness ahead of time and be able to predict the free spectral range of just a really large interferometer?
Yeah, so I think there's 2 parts to the question. Maybe I'll start with the first thought is, what happens if you have a very long interferometer, like a traveling wave, high speed, 4 millimeter long interferometer? So you can draw that in this tool, and if you draw the waveguides, say 3 microns apart, what you'll find out is that they're very well phase matched, because all the variations, essentially, it's like 2 waveguides going up and down the mountains together. And there, the phase error between those 2 waveguides will be very small. But if you draw, but if you have massive electrodes and you have to separate them by 100 microns, then the phase errors between those waveguides will accumulate larger phase error. And so in terms of, if for modulators, high-speed modulators, I think pretty much all Mach-Zehnder modulators require some sort of tuning. And typically you buy a little box that biases the modulator at quadrature or something like that. And so there's always an offset point in terms of where the sweet spot is for the modulator. So, but your second point is very interesting, which is, can you measure it beforehand and then either selectively fabricate on a part of the wafer that's more flat, or at least predict what's going to happen? So I think that's possible. There's one challenge with that, in that it's not just the thickness variation that kills you, but it's also the width fluctuations that kill you. And so in the work that we've done, when we've extracted the variability of structures, we find that it's roughly an equal contribution from the width variation as from the thickness variations. And so you're only going to get a factor of kind of 2 better. So people have resonators with wider waveguides, Bragg gratings with wide waveguides, and shown that you can reduce the variability by roughly a factor of 2, but it doesn't completely go away because now you have thickness. So you can try to get rid of the width problem by making it wider. The thickness problem still remains. If you solve the thickness, you have to solve the other ones. So, and then the variation of the width is a bit of a mystery in terms of exactly where it's coming from. Some of it has to do with the chemistry and the etching and proximity effects, something called etch loading. When you're removing materials, you're depleting chemicals. And so if you have lots of structures, like if you're close to some other waveguide, you might etch slower, whereas if you have a waveguide isolated by itself, it'll etch quicker. So that's one possibility. And then there's, who knows, there's a bunch of other things that could be happening as well. So,
or maybe you're getting near the edge of your field of view and your E-beam is different or whatever, right?
Yeah, it could be E-beam, beam current, things like that. Actually, the photoresist or the electron resist thickness could also be changing thickness, which will lead to different exposures and different feature width at the end of the day.
Sure.
So there is a translation to feature width from numerous fabrication process steps. So I think I was at some point in time I was excited about your suggestion, which is, can you measure things ahead of time and then fabricate them better? And I think I've concluded that you might be able to do better, but it's not going to be 10 times better probably. And what we really need in some of the research I'm working on is, I need about a factor of 1 million. So our fabrication is about 1 million times worse than what I need for my application. And so realistically, that's never going to happen. And so what we're stuck with is some sort of tuning mechanisms to solve these problems.
Okay, thanks for engaging the question.
Yeah, my pleasure. Yeah, that's a very fun topic. Okay, anybody else have some questions?
Probably answered with what someone is about creating the text file himself.
Yeah, exactly. So I think Payam had a question about S parameters. So I think that's for Payam's question, refer to that example. That's a good one too. Yes, go ahead. Hello, Jenderson. Yes.
Hi, Lucas. Are you hearing me?
Yes, we hear you. Go ahead.
Oh, I have a question about our design. So far, for what we have seen, the waveguide has oxide on the top, oxide layer on the top, but the grating doesn't have. So I'm a little bit confused about that.
Okay, sure. So there's choices in terms of manufacturing. We can the way the fabrication process works is that you have a layer of silicon that's sitting on oxide, yes, and then we transfer the pattern to the silicon, and then you have a choice of either covering the whole thing with oxide or not covering it, or covering it and removing the oxide as well. So there's 3 versions of the process that we can do. In this course, what we're going to do is we're going to cover everything with oxide. And so the grating coupler will be covered in oxide, and the waveguide will be covered in oxide. So I think your question was probably looking at one of the videos or pictures of the grating couplers. We have some grating couplers that are exposed to the air and some that are exposed to or covered in oxide. That's a choice that we have in the fabrication.
Okay, okay, thank you.
Yeah, you're welcome.
Hello, Professor.
Hello, Nane.
Hello. I have two questions. My first question is about finding FSR in diagram. You know that there are several formulas that we can use them to find FSR. For example, FSR is equal to delta lambda, or lambda squared divided by delta L multiplied to x. And according to your simulation in video minute 3 and second 46, here we see many points, but later in video we see that you find FSR by formula. How can we find FSR from diagram among many points directly? Thank you. I have your picture. Yes. Here is picture.
Okay. Did you understand that?
Yeah, he was asking like there's a formula for the FSR,
Yeah.
and you can extract
Sure.
can extract the FSR from the figure directly.
From the figure. You mean from when you do a simulation?
Is it from the simulation?
Yes, yes.
Okay. Okay. So let me repeat the question and see if we're correct. So we theoretically we can calculate the free spectral range if we know the group index and the path length difference. But when we perform a simulation either in MATLAB or Lumerical Interconnect, we get a spectrum. And how do we extract the FSR from experimental data or simulation data? Is that the question?
From simulation data. My second question is about how to find coupling loss in person.
Sorry, Nani, do you want us to answer the first question on how to extract the FSR? Do you want me to give you a demonstration of how to do that, or?
Yes.
Okay, so let me describe in words, and then maybe in the discussion forum we can give you more specific steps on how to do it. So in MATLAB, it's possible to do curve fitting of the spectrum. If you know the equation, then you can do a curve fitting of it. That's number one. Number two is you can find the peaks, and the MATLAB has a function called find peaks, which allows you to essentially discover where they are and then perform the difference. And then in Lumerical Interconnect, when you use the optical network analyzer, it displays the spectrum. But if you look in the results viewer, there's also a section in there that talks about the peaks. And it actually measures the FSR directly within the software as well. So I think there's a few different techniques. There's going to be a module on finding the FSR from the experimental data. And that's going to occur after you submit your design. So after you submit your design and we manufacture it, we're going to give you some experimental data to practice with, including a bunch of spectra and curve fitting to extract the peaks and extract the FSR from that. So, so I guess there'll be a very long answer to your question. That's about a 1 week answer, probably 3 weeks from now, roughly. Okay, Nanu just left. Okay, so he missed the answer. He can watch the video after. Okay. Okay. Any other questions?
I'm not going to ask this one very well, but I think some of my students were telling me that when they did the mode overlap calculations for one of the homework problems, they were getting a slightly different result than what you had posted. Maybe we're wondering if there's a numerical update that.
Yeah, so that's a tough one. It seems like a lot of people are complaining about that they're not getting exactly the right answer. So the question is my answer correct, or is your answer correct? I guess I don't know. So the way I guess there's a couple of points that I can say. One is that different machines give you slightly different answers because of whether it's 32 bits or 64 bits, things like that. There's also variation between the different versions where things may have changed a little bit. So those are things that are a little bit outside of our control, and I hope that variation should be very small.
Yeah, it's very small, but they were all getting the same wrong small answer, so or the same.
Yeah, so that's probably because I was running a version from a couple of years ago, and something may have changed a little bit in the models. So that I wouldn't worry about. I mean, don't expect the same answer. In terms of the accuracy that I really ask people to get compared to my answer is it should be manufacturing variability. And so manufacturing variability gives us, something like 0.1 change in effective index or 0.1 in group index. So we're getting really on the scale of 5%, 10% variation in all the parameters that we get. And so if the error is 1% compared to mine, or 0.1% compared to mine, then that's good enough. That's noise compared to the experimental uncertainty. But if there's something where I have an autograder and you have to type in the answer, and I ask you for 6 significant digits, and you get the wrong one, and that's because I don't want to be doing that. So.
That's what we expected.
Okay, great. Hello, Hiva. We can hear you throwing things out.
Yes, sure. I have a question. Can you hear me well?
Yes, go ahead.
Okay. You were talking about the heaters and how great to have them in a design in order to adjust the structure, like the structure we want. So can we have heaters on or MZI branches? I mean, for this course?
So in this course, we are doing fabrication that does not involve any metal, number one. And the reason we're not fabricating metal is because testing it is a lot more work. So we have an automated probe station that essentially can measure 5,000 devices in a day simply by moving the chip around or moving the fiber array around. But it's a lot more difficult to automate fibers at the same time and pick up the probes up and down, and do that across the board. And then furthermore, it becomes more challenging in terms of, well, what does everybody want to do? Blow up. I think the combination of electrical and optical testing is something that is not straightforward to do in an online course with 100 people in it. But that said, I definitely have an interest in Hassam, as an example, does this for his research. So he has lots of interferometers with heaters on there. So it's definitely doable, but it's that's something that you may want to do in the lab yourself, for example.
What about PN junctions? Can we have them for like modulators?
Yeah, so the same answer.
Them on MCI for
yeah, so the same answer. So in this course, we're keeping the fabrication simple, where we only do the passive structures. But it is possible to fabricate them, of course, and there are lots of foundries around the world. We have IMEC, IME, AIM Photonics, LEDI. There's probably about 10 foundries in the world that can do PN junctions right now, and PIN junctions, germanium, and all these other active parts. So it's possible to do, it's possible to test it, but it makes it much more difficult in a very short course.
I see.
So that's if you have an interest in getting chips made and getting those kind of chips. Unfortunately, the timing, we just missed it, but 2 weeks ago we had a course, a 5-day in-person course, where we covered the design of PN junctions and heaters and all that kind of stuff, as well as the measurements. But that course essentially is a 1-year-long course, because the factories typically take a year to make those chips.
Okay. Like the other question is, can we have fiber Bragg gratings at the end of branches instead of mirror?
Instead of using a loop mirror, or like a
loop mirror.
Yeah, sure. You can use a Bragg grating. Yeah. So I just showed an example in half an hour ago of looking at Bragg gratings. And you have the compact models for the Bragg gratings, so you can perform circuit simulation. You can absolutely build a micro-sum spectrometer with Bragg gratings. And there's a really nice paper from a group at McGill University that actually did essentially something along those lines, where they built a Michelson interferometer with Bragg gratings. So I can, if you post something, we can try to find it for you and give you the reference for that. So
Thank you.
you're welcome.
Hello, Dr. Lucas.
Yes, hello, Omar.
I've joined a little bit, but I have some questions. I want first to ask about this week material. We start the week by creating models of interferometers and simulate the interferometer circuit in numerical interconnect software, and then we use a compact model library to simulate it again. I don't understand why is that? Why do we do that?
You want to know why are we using a library? You're wondering, or?
Yeah. We're using a library again to simulate the circuit.
Yeah. So the idea of libraries is that we want silicon photonics to proceed in a style similar to the electronics industry, where components and libraries. And then you have another group of people who take those components and play Lego with them and connect them to make circuits. And so we're going to have component and library developers and then circuit designers who use those components. And so that's the reason why we separate those two into two separate kind of categories.
So do you mean that we first take the sense of doing the models and then use a ready library for our devices?
That's right, exactly. Yeah. So to make sure that your simulations work correctly, rather than having a prerequisite where you've made your own component model, we give you the component model so you can make a circuit out of it. Now, in principle, you could start from scratch and not use my library. You could start with your components, bits with those. So that's certainly possible.
Okay, that's fine.
Yes.
I want to ask two more questions, please.
Okay.
About the price of the chip we will fabricate. How much will it cost if I wanted to purchase it?
Yeah. So if you want to purchase your own chip, if you go to the webpage for Applied Nanotools, they have an online calculator that will give you a quotation for how much the chip costs. It's roughly $1,500 for the whole chip.
Oh, can you give me the link for that calculator?
Sure. Yeah. We can post it on the discussion forum. So if you post something, and we'll respond to you.
Okay, that's good. The third question, please, about the future fabrication cycles, and if I have another idea that I can't implement it in this 2 months period, and I wanted to make it in the future.
Mm-hmm.
Will
sure.
So
there's two options. So in terms of the electron beam fabrication, we're going to be fabricating chips every 2 months. So every 2 months, there'll be a fabrication run where you can submit and purchase your own chip. And also what we do is, for the students who've taken this course already, is you can essentially keep submitting it. The next time this course is offered, you can come back and resubmit something again. So you won't get access to all the software and all the licensed tools, but we'll find you and test it for you. So at the end of the course, I'll provide you a link, and we usually advertise this on LinkedIn and the other places like that.
Okay, thank you.
You're welcome. Okay, so unfortunately, I need to run, so this is the end of my time. Thank you very much, everyone, for joining this morning, or this afternoon, or this evening, whatever time it is for you. If you have any additional questions, please post them on the discussion forum. So Hassam and I are enjoying seeing all your questions, and we wish you lots of good luck with your project. We hope that your component and circuit modeling is coming well, and next week we'll begin the really fun part of creating the physical structures and then simulating those. And essentially for the next 2 weeks, you'll be working on your project to create a physical implementation of your design. So thank you, everyone, and until next time.